All right, section 7.3 has to do with the scalar or dot product. And we're talking about this now because one of the best examples of this is work. We're going to talk about it in that context. So we define the dot product of two vectors A and B. The dot product of A times B is given by, no surprise if you just watched the video on work, the absolute value of A, or the magnitude of A times the magnitude of B, cosine theta, where theta is the angle between A and B. All right, this is the definition that's like a projection. So if we look at the idea of viewing it as a projection, let's imagine B and A like this, and cosine theta here. If we define a coordinate system in the direction of A, so I'm going to call it little a hat for that direction, and then this would be, or let's not use weird notation. Let's just call that our x direction and this our y direction. All right, so if I talk about the vector A is just equal to magnitude A times I, because remember, I is the unit vector in the direction of x. And then B will have some components in the x direction and the y direction, right? So I'm going to call that bx times I plus by times j. And if we were to look at the x component of B, we know that bx will be equal to b times cosine theta, because that's the adjacent side of this triangle. But you'll notice that that's exactly what we have in our dot product if we take A dot B, we get A, B, cosine theta. So this idea of a projection, and particularly when we talk about it with work, it's the part of force that's in the direction of the displacement, or it's the part of the displacement that's in the direction of the force. A lot of times we think of the force as the instigator of the motion. So we might think about part of the force acting in the direction of the motion as natural. But sometimes it makes sense to think about the part of the displacement that's in the direction of the force, because you have something like gravity, where the force is always down. So it's convenient to think about the portion of the displacement in the direction of the force. And we'll do that in detail when we talk about gravity. But I just want to point out here that we arbitrarily chose A as our x direction. We could have chosen B as our x direction and done the same thing. So the idea of a projection is very clear the way that I've drawn this example, but we just talked about angles over 180. So if we look at that and we talk about a projection, then we would have to extend B backward and project A down. And you see that the projection of A onto B in this case is in the negative B direction. And that's how you get that result. All right. So let's talk a little bit about the other notation for the scalar product. What you might call the more sophisticated notation. So we've already said that if I have some three-dimensional vector A, I can say it's AX times I plus AY times J plus AZ times K, where IJ and K are my three-dimensional spatial dimensional vectors. And B is BXI plus BYJ plus BZK. So if we want to then take a dot product of A times B, we need to talk about how our elementary unit vectors react under a dot product. So let's look at, we have a coordinate system here, X, Y, Z, and our elementary unit vectors point along those axes, and they're magnitude 1. So if I were to look at, for example, I dot J, well, my coordinate axes are all perpendicular to each other. So this would be magnitude I, magnitude J, times cosine 90. And cosine 90 we know is 0. So this is actually true for each combination, because we know they're all perpendicular. What if I do I dot I, or J dot J, or K dot K? Well, we have I, magnitude I, cosine 0, because I is in the same direction. All right, in this case, we see that that's just 1, because these are unit vectors, so the magnitudes are 1, and the cosine of 0 is 1. And this is true for each pair of unit vectors. And this introduces a notation you can use with a Kronecker delta. You could say EI, EJ is equal to delta IJ. This Kronecker delta is defined to be 1 when I equals J, and 0 when I is not equal to J. And these are not the unit vectors I and J here, they're just indices. So maybe I should have used different indices, but it's traditional to just use I and J for your indices as well. All right, so now we can talk about what A dot B is if we have it written in component form or expanded form, or however you think about that. So So we can look at the dot product here as distributing just like you would if you were multiplying scalar values. So I've got AXI dot BXI plus AXI dot BYJ plus AXI dot BZK. And that's just the first term dotted in, right? So then plus AYI dot BXI plus AYI dot BYJ. Oh, should have been J, sorry. I put I's everywhere just because I was going too quickly. And AYJ dot BZK. AZK dot BXI. I'll never write this all out again. I'm just doing it now to make a point. All right, it's all written out, right? We have 2 3-term things with a product. So there's 9 combinations. We have 9 terms in the product. But we just talked about how these dot products work. We can take these scalar values out and we're just dotting the vector parts, which are our unit vectors here, right? So if we look at that, we said that it's equal to 1 if the indices are the same, and it's equal to 0 if they're not. So the only terms that are non-zero are these terms. So, and we also know that I dot I is 1, J dot J is 1, and K dot K is 1. So we end up with AX BX plus AY BY plus AZ BZ. And you'll note that this is a scalar. It is no longer a vector. So that's why the dot product is called the scalar product, because you take 2 vectors and you multiply them together in such a way that you get a scalar quantity. All right, what else do I want to say about the scalar product right now? Let's look at a 2D example and convince ourselves that our cosine approximation is sufficient. We can do it in 3D, but it takes a bit more math than we want to probably do. I think you have to use a law of cosines to do it. Well, we kind of already talked about projections, and that's pretty much all you have to do. Right? Let's see. Yeah, we pretty much already talked about it. Just choose your coordinate axes so that one of them is on it, and then you're just projecting onto it. There's not much to it. All right, we said before that if we choose our coordinate axis X in the Y direction, then in the A direction, sorry. I was writing the Y when I said it. Then we just have AX times I plus 0J for our A vector. And our B vector then gives us BXI plus BYJ. And now if we use our component definition of the scalar product here, we see that we just multiply these. And we know that BX is just B cosine theta for the projection onto A. So in general, though, you can do it for as many terms as you have. If I have a vector, what do I want to start with? Let's say 3i plus 4j. And let's say B is a 45-degree angle. And I want to take a dot product. Well, we have 3 times 2 plus 4 times 2. 6 and 8, 14. How would we do that looking at a projection of one onto the other? It'd be a bit more difficult, right, if we want to find the angle between these. So if I have my coordinate axis here, this is at 2, 2. This is at 4, 3, or 3, 4, sorry. Get my axes labeled. All right, so this angle we said was 45. This angle is, it's a 3, 4, 5 triangle, which means 37 and 53. So that's a 53-degree angle. So if we were to look at the angle between them, it would be about 8 degrees. And we need the magnitude of the two. So this was 2 and 2, so square root of 8, which would be 2 square root of 2. And this one's 5. I chose a 3, 4, 5 triangle for that reason. So if we were to look at it now, we would have 5 times 2 square root of 2 times cosine 8 degrees. And the 8 degrees is rounded a bit, so we're not going to get 14 exactly, but it'll be close. 5 times 2 square root of 2 times cosine 8. Yeah, I got 14.07. To 2 sig figs, it's fine. Right, so that's just a numerical example of how you could arrive at, but how it's much more difficult to actually get it if you're given the component form to find it in terms of the vectors. But a lot of the time we have the vectors, so the cosine form will be useful. Do I want to talk about varying, or is that in a different section? Yeah, the next one we'll talk about work done by a varying force. So all this that we've talked about so far has assumed that the force is constant, and we can look at the force and displacement and the angle between them, and that doesn't change. So in the next section, we're going to look at a varying force.